Hi, my name is Ward Alababne, and today I will be talking about a lesson explaining a problem and solving a problem. I'm studying mechanical engineering currently at the University of Mount Union, and in statics and dynamics, this is the book that we're using. It's called Engineering Mechanics, Statics and Dynamics, 14th edition. So I was asked to do the 14.6 lesson, which is called the conservation of energy. First of all, I'm gonna explain to you what the conservation of energy is. It is the principle stating that energy cannot be created or destroyed, but it can be altered from one form to another. It can also be used to solve problems involving velocity, displacement, and conservation force system. So conservation of energy has 4 principles, and I'll be listing them all. So 1, we have mass energy, which is E is equal to mc squared. Second one, mechanics, problem solving. Third is work, energy, principle. And fourthly, role as fundamental principle. So, conservation of energy requires specifying the particulars and potential energies at only 2 points. So when we have a particle and it's acted upon by a system of conservable and not conservative, the work can be written as this: T1 plus V1 plus sum of forces V1 minus 2 is equal to T2 plus V2. We have also a similar one that we can also use, which is the sum of forces T1 plus sum of forces of V1 is equal to the sum of forces of T2 plus the sum of forces of V2. Sum of forces of V1 minus 2 represents the work of the non-conservative forces acting on the particular. So when we only have conservative work, the equation will be as this: T1 plus V1 is equal to T2 plus V2. And this is called the conservation of mechanical energy, which means during the motion, the sum of kinetic and potential energies are constant. I'm going to give you guys an example right now. Let me just erase this real quick. So I'm doing example 14.10. So we have this figure right here. So this is a ram that has a mass of 100 kilograms, and it is released from rest at 0.75 meters from the top of a spring. A, which I will be showing you right now, these are the measures right here, top of this. This is 0.75 5 meters. From here to the second one, and from here is 0.3, but all of this is 0.4. We've got KB is equal to 15 kilonewtons per meter, and K of A is equal to 12 kilonewtons per meter. So as I said, this is A, and this is B. So A, that has a stiffness of 12 kilonewtons, and B has a stiffness of 15 kilonewtons. So now we want to come here and solve the problem. A is compressed by the distance, and B compresses CB, which is equal to CA minus 0.1. So to solve this problem, we're going to use our conservation of energy equation, which is T1 plus V1 is equal to T2 plus V2. To solve this problem, T1 is 0 plus V1 is 0, which is equal to T2, which is also 0, plus the V2, which is 1 over 2 K of A S2A plus 1 over 2 K B, and then S of A minus 0.1 squared minus the weight of H. So to come and solve this problem, we will get 0 plus 0 is equal to 0 plus 1 over 2 times 12,000 newtons. 12,000 newtons, we converted it from the kilonewtons to newtons, which you just multiply by 1,000 newtons per meter squared. And then you got S of A plus 1 over 2, 15,000 newtons per meter. And then you've got the S of A minus 0.1 meters squared minus 981 times 0.75 plus of SA. The 981, it came from our it came from our gravity, which is 9.81, and we just multiplied it by 100. So to solve this problem, we would get 13,500 S of 2A minus 2,481 SA minus 660.75, which is equal to 0. Using the quadratic formula, we want to find S of A. S of A would be 0.331 meters. So our final diagram would be like this. Since it's compressing the A and the B, sorry about that, we're gonna have a compressor here and a compressor also here as it's in motion. So the gravity acting on it is 981 newtons. Also this gravity is the same, which is 981 newtons. And from here, from this top to this, from this top to this bottom is still 0.75 meters. This is that, and we still have this that's been compressed. So this is SA, and this is SB, which is SA minus 0.1. So this is our example. So, let's come to the final problem and solve it. So I'm solving 1467, which it says right here, the 30 pounds block A is placed on top of two nested springs B and C and then pushed down to the position shown. If it is then released, we gotta determine the maximum height H to which it will rise. So let's erase this real quick. Let's solve this problem, which is, we said 1467. So first of all, we gotta draw our diagram. We have block A, and we have, this shows block A has been compressed. We have also another one right here. Then we've got the height from here to here is 6 inches, and the height from here to the end is 4 inches. We've got K of B is equals to 200 pounds per inches, and here K of C is equal to 100 pounds per inch. This is C, this is B, and here we have the height between this and the middle of this, which is the unknown. We gotta find our maximum height, which is this, when it will rise. So to solve this problem, obviously, we're also gonna use our conservation of energy equation, which you guys will probably know it by now. T1 plus V1 equal to T2 plus V2. We have half of mv1 squared plus v gravity 1 plus v e to 1 is equal to 1/2 of mv2 squared plus, let's put this right here, plus v2 plus v2, and then we will get 0 plus 0 plus 1/2 of 200 times the 4, which is the distance, plus also 1/2 of 100. As you shown right here, this is K of C, and this is K of B. We use the 200 and 100 to solve this, and the distance between that is 6 inches, as we said, squared. So our height is going to be 0 if we add all of these together. Height times 30 plus 0. Our height is in inches and 113 inch. And by this, I just completed and explained our lesson, solved the problem, and also explained the problem. Thank you so much.